the last couple of years, we've been doing a soil health project thanks to sponsorship of Ohio Soybean Council. When we look at those different soil health properties, and this project that we've done, we're in our third year on it, where we're sampling now at just that 8-inch depth, which allows us to look at our traditional soil nutrients, so phosphorus, potassium, potentially magnesium, pH, those standard soil test values, but also look at these soil health values, see if there's any correlation between them, and also look at how soil health compares. An important thing to think about though, when you take these results and use them on your own farm, we do have some graphs on there that compare you to state averages. But the real thing with soil health isn't how do I rank up against somebody else, it's how does my soil change over time? How is my management affecting soil health, not where do I rank? And this study continues to show us that there's archaic factors about soil health we're not really going to change very fast. One of those being CEC, and then what those original parent materials are. How much sand do we have? How much silt do we have? Really is like that overarching effect on soil health, but we can do a lot to affect soil health after that. So an additional part of the project is looking at yield and correlating that to soil health values. So when we start to look at the different soil health factors on the report, on the first set there are your aggregate stabilities. So you have micro aggregates, macro aggregates, and total aggregates for that aggregate stability value. When we think about aggregate stability, why does that matter? Well, aggregate stability is a measure of how structurally sound your soil is, which affects how much it can erode, but also how well nutrients bind to it. So when we think about micros versus macro aggregates, what do we want more of? Well, we really want more of the larger particles, those macro aggregates. We want the little bit bigger particles. Aggregates are a measure of that glue which comes from the organic matter in the soil and how well they're held together. So if we think about a really small aggregate, when we get a heavy rainfall event, if there's nothing there to protect our soil, that heavy rainfall event takes those really small aggregates and washes them down into our air pore space. And then that helps to cause that soil compaction. And it decreases our air and water movement and interaction throughout the soil, because we need a soil that water will infiltrate through but doesn't stay waterlogged, because when it's waterlogged, roots are like us. They're not fish. They can't breathe. They don't have gills. So if we have a waterlogged soil that has a lot of really small aggregates in it, it can't breathe and those roots won't survive. And the larger aggregates have more glue in them, so they have more organic matter and they hold together better. But there's an important little challenge that comes with aggregate stability. So if you would pull these samples yourself, when you think about pulling a soil sample, a lot of times you put it in a bucket, you let it dry, and then you mash it all up and bring it all together and pull a subsample. Well, when we do that with aggregate stability, if we dry that soil and we beat it up too much, we actually break those aggregates down, similar to a rainfall event or doing tillage. Tillage actually breaks soil aggregates. And it creates soil aggregates. It changes their size. And we do the same thing, so then our soil aggregate values can be wrong. So if you go and pull a soil aggregate stability test on your own, that's an important thing to remember, so you don't damage that aggregate. And that's been one of the things we've worked on, is to make sure everyone knows that when they pull that, they submit an entire core, and they don't beat that up like a normal soil sample. But aggregate stability really gets to how stable our soil is and how well it's going to resist rainfall, and potentially hold up to tillage and different events like that. And you want more big aggregate. The next value to consider as we come down through that test is going to be POXC. That's kind of a newer one. It's actually strongly correlated to soil organic matter, because POXC is a measure of the active carbon in the soil. And really that's what organic matter is. It's a measure of carbon, but not active carbon. Well, active carbon responds quickly. Soil organic matter, typically it takes years to see a 1% change in soil organic matter. But active carbon, on the other hand, it'll respond to changes in management in 1 or 2 years, because that's the part that's really doing the work, interacting with your nutrients, binding nutrients, and that's the carbon that was just made by the microbes out of your plant material as it decomposes and things. So that's that workhorse of the carbon fraction, and that really tells you if that is going positive, if you're increasing active carbon, you're doing things that will eventually build soil organic matter. But it's one that you can tell in a timely fashion if your management is affecting that organic matter. And then as we look down through, the next few are just those typical mineral nutrients, things like CEC, which is strongly correlated actually to all of our soil health factors. That aggregate stability and POXC have a correlation to CEC. The higher the CEC, the higher the POXC. So then we get down to respiration, or parts per million of CO2. And that's another one that we're graphing against the whole state average from the program. Aggregate stability is one that's very hard to compare field to field, really CEC dependent. CO2 is very much dependent on that microbial activity. So what they do is they put the soil into a canister and they measure how much CO2 is released from that soil. So it truly measures living life in the soil that is respirating or releasing CO2. What does that mean? So the more activity we have, the more decomposition we're going to have of plant material in that field. So high respiration is a good thing. Now, just because you have low respiration doesn't mean it's bad. It can be effective time of year even compared to another sample. So with soil health properties, if you want to compare your field over time, it's really important to try to sample about the same time every year. So when we think about respiration and decomposition, so if we would go out and do tillage, we'll actually take a tilled field and we'll really increase soil respiration, or we put livestock manure on that field. We can actually really increase soil respiration for a short term, and once they get done decomposing, they're going to crash. And then we're going to see a decrease in respiration. A long-term no-till organic or a no-till cover crop field that just always has plant residue that's feeding those soil microbes, it may have a more consistent CO2 release. So when we think about how to use soil health results, you can somewhat compare a few things maybe to your neighbor. But the real thing is, how does it change over time on your farm? Are you making positive changes? So when we look at yield is of both corn and soybeans is positively correlated to POXC. Why is that? Well, more organic matter is going to have more soil nitrogen. More active organic matter going to be releasing more soil nitrogen. So it makes very intuitive sense for corn to be highly correlated to POXC. Soybeans is fairly flatlined to POXC. On the other hand, soybeans have a positive correlation to CO2 respiration. Corn just kind of hangs out with CO2 respiration, either positive or negative, maybe slightly positive to more respiration. But soybeans really ramp up and you see a yield increase from increased CO2 respiration. Well, soybeans don't need nitrogen because they're going to make their own, so no relation to POXC makes sense there. Soybeans may benefit actually from a little bit more CO2. There's some studies out there where they grew soybeans in CO2 chambers, and extra CO2 is extra plant food. So maybe that's why we see that slight. We don't really know exactly what that relationship is. We just know that more respiration slightly increased soybean yield. And the same thing with some other soil health factors. So manure, positive for corn and soybeans, and positive for all of our soil health factors. When you put manure on, it's positive for yield and soil health. When we grow cover crops, it's positive for soil health, it's positive for soybeans, but it was flatlined to negative for corn. Why? That probably comes back to we're maybe tying up nitrogen, and in a statewide survey, we're not really capturing that nitrogen tie-up to figure that out in yield effect. Other things to look at, no-till. No-till's got a flat line to slightly positive in soybeans, but unfortunately, no-till alone, slightly negative correlation actually to both soil health and corn yield. Why is that? Well, when we look at no-till, we actually see slightly decreased soil respiration, but if we put a cover crop into the system, it changes that. All of a sudden, respiration goes back up, and we're flatlined to positive on that no-till factor. It comes back down to, especially on the corn side, no-till, we may not quite have that environment, and over time we see a change in aggregates, even in no-till, where we get more and more small aggregates, and we don't quite get that air exchange maybe that we want. So putting things together in a system really is what leads to that soil health and maybe potential for some yield increases. So remember, when you look at these results, while the graphs are compared to that state average, the real important thing is to participate in this study 1 year and then go out and continue it on your own every couple of years and compare how your management on your fields is changing them, so you can continue to make those dynamic management changes to meet your goals.